Okay, moving on to continuity. So in some of our previous videos, we had a two-sided limit that failed to exist because the one-sided limits from the left and the right did not agree with each other. And in these instances, and in several others, we have what we're calling a discontinuity. So remember that we can determine a function is continuous at a point if the function is not continuous at that point. Discontinuities fall into two categories, removable and non-removable. A removable discontinuity would be a point discontinuity or a hole. And by removable, we can redefine the function to fill that hole. A non-removable discontinuity would be a jump or an asymptote, vertical asymptote. So discontinuities are the interesting parts of the function and are really going to be the focus of most of the calculus that we're going to be doing. So conversely, if the function is continuous and doesn't have any gaps, jumps, or holes, we have the benefit of being able to make some fairly straightforward conclusions. So the formal definition of continuity consists of three parts, and I say that it's likely you will need to know these in this order. In order for a function to be continuous, the function must exist for some x, which means that f of c exists. The limit of the function that exists for that x, the limit of the function exists for that x, so the limit as x approaches c of f of x exists. And the function value equals the limit of the function, which means the limit as x approaches c of f of x equals f of c. This means that my limit as x approaches c from the left of f of x has to equal my limit as x approaches c from the right of f of x. So looking at example 1, we're going to identify the points of discontinuity and state which condition fails. So we can see that our point of discontinuity is at x equals 2. And the condition that is not satisfied is that the function is not defined at 2. So if we wanted to define a function that has a removable discontinuity, so here's an example. F of x is equal to x squared minus 2x minus 3 over x plus 1. And we can see that then that simplifies to x minus 3, x plus 1 over x plus 1, and we have a removable discontinuity at x equals -1. So to define a function that has a non-removable discontinuity, we could do f of x is 1 over x squared minus 25, and we have vertical asymptotes at x equals 5 and x equals -5. All right, so why is continuity so important? Okay, so when a function is continuous at a point, then the limit of the function must be equal to the function values, based on the third part. Given this, we really need to know which function families are continuous and over what intervals. So polynomials, anything with a natural number power of x, a whole number power, not natural number, whole number power. So 3, 4, 5, 2, things like that. Radicals are continuous, but they are continuous on their domain. So j of x is continuous on all real numbers, but h of x is only continuous for x greater than or equal to 1/2. Okay, so other functions that we're going to work with, rational functions, they have fractions in them. Those obviously potentially have discontinuities. Trigonometric functions, sine x, cosine x, and so on. Remember that sine x and cosine x are going to be always continuous. Logarithmic functions, natural log of x plus 5, things like that. exponential functions, e to the x, which is always continuous, 2 to the negative x, also always continuous. So trig functions are continuous over their domain. So sine x and cosine x are continuous on all real numbers. Things like tangent, cotangent, secant, and cosecant have discontinuities, but they are continuous over their domain. All right, so if we need to identify some points of discontinuity, all right, let me back up. Okay, so often we need to determine the continuity or evaluate the limit of a piecewise function. And we did some of this in class. So remember that a function must meet all three criteria in order to be continuous at a particular value of x. And that in order for a two-sided limit to exist, the two one-sided must exist and agree with each other. So looking at example 2, we can see that we have a discontinuity at x equals -2, and that's going to be a hole, and that is a removable at x equals -2, and that point is then going to be -2, -4. And the conditions that aren't satisfied, f of -2 does not exist. All right, so let's take a look at the absolute value of x minus 2 over x minus 2. You can see that you have a jump discontinuity, which is also non-removable. So we have a jump at x equals 2. And we have again then our limit as x approaches 2 from the left of f of x. I can see equals 1. And the limit as x approaches 2 from the right of f of x equals -1. So therefore the limit as x approaches 2 of f of x does not exist. This also fails f of 2 does not exist, and there are open circles at both of these. Okay, so let's go ahead and take a look at this last one. So we have there are no discontinuities that we can see because this is a polynomial and this is a polynomial. So now we need to check our left-hand limits. So the limit as x approaches 0 from the left, and this is going to be of -x plus 1 squared plus 3. So we substitute in 0, and so we have 1 squared negative, so that becomes a +2. And then our limit as x approaches 0 from the right of 2x plus 2 also equals 2. And so our limit as x approaches 0 of f of x equals 2. And then we can see then that looking at this one, that f of 0 equals 2. Therefore, that function is continuous. We are going to work on example 3 in class.